the arrangement of atoms, something related to the spatial arrangements, the bonds, all of that are different, but these compounds will have the same molecular formula if it is a bidentate ligand. So for example, we have taken EN here, that is ethane 1,2-diamine. So in that case, how will you write the geometrical isomerism cis and trans? Let's take the example of COCl2 EN twice. The plane polarized light, if it is rotated towards the right by the compound, it is called as dextro. Hello everyone, this is Amli Unnikrishnan from the Department of Chemistry. So today we are back with session 3 of the chapter Coordination Compounds, right? So in the last session, we studied about what is coordination sphere, what is coordination polyhedron, and oxidation number of central atom, how to calculate oxidation number, and the table of common ligands, which are the monodentate ligands, which are the bidentate ligands, which are anionic, cationic, and neutral, right? As well as the nomenclature of coordination compounds in detail we studied in the last session, right? So in today's session, we are going to discuss about isomerism in coordination compounds. So you are already familiar with what is isomerism, right? So in coordination compounds, how does this isomerism acts, we are going to see, right? And then what is stereoisomerism and structural isomerism? Those are the different types of isomerism. Under stereoisomerism itself, you have 2 types, and structural isomerism, you have 4 types. So all of this in detail, we are going to study in this session, right? So first, let us begin with the different types of isomerism shown by coordination compounds. So there are majorly 2 types. One is stereoisomerism and one is structural isomerism. So stereoisomerism are of 2 types, geometrical isomerism and optical isomerism. And structural isomerism is of 4 types, linkage isomerism, coordination isomerism, ionization isomerism, and solvate isomerism. So all of this in detail we are going to study in this session, right? So beginning with the isomerism, isomers are 2 or more compounds that have the same chemical formula, right? So we already know this definition about isomers. They are different compounds having the same molecular formula, right? But something else is differing, right? So the chemical formula is same, but a different arrangement of atoms. Right, the arrangement of atoms, something related to the spatial arrangements, the bonds, all of that are different, but these compounds will have the same molecular formula. That means the same number of atoms will be present. It's just the arrangement of the atoms will be different, right? Because of the different arrangement, they differ in one or more physical properties and chemical properties. So of course, they are different compounds itself having different physical and chemical properties, right? So there are majorly of 2 types, stereoisomerism and structural isomerism. So the first one is stereoisomerism. They have the same chemical formula. Again, they have the same chemical formula and chemical bonds, but they have different spatial arrangement. So what they are differing in the spatial arrangement of these atoms, right? Chemical formula will be same, the bonds will be also same, but the spatial arrangement will be different. There is geometrical isomerism and optical isomerism. Now structural isomerism means they have again same chemical formula, but they have different chemical bonds, okay? How the bonds are formed will be different. Based on that, we have linkage isomerism, coordination, ionization, and solvate isomerism. So beginning with the first one, that is stereoisomerism. Okay, the first one in stereoisomer is geometrical isomerism. So it is a phenomenon in which 2 complex compounds, right? 2 different coordination compounds have the same molecular formula and same chemical bonds also, but differ in their geometrical arrangement of ligands. Okay, so we are talking about coordination compounds means ligands will be present. So how these ligands are arranged in space will be different. Their geometrical arrangement will be different. So such compounds, right? Such coordination compounds are shown, are said to have geometrical isomerism. So the 2 forms are called as cis and trans forms. So this geometrical isomers are called as cis isomer and trans isomer, generally found with compounds having coordination number 4 and 6. Okay, so which are these isomers? This is cis isomer and trans isomer is there. How to write those isomers we are going to study now. So now in the first one we are going to see in a square planar complex. So square planar complex means coordination number will be 4. We have already studied this. So coordination number will be 4 means there will be 4 ligands which is present, right? So complex with formula mx2l2. Okay, M stands for the central metal ion. X and L are two different ligands, right? So it is given that both of them are monodentate or unidentate. Exhibits geometrical isomerism. One will be cis isomer and one will be trans isomer. So let us take an example and understand what is this cis and trans. PTNH3 twice Cl2. So we are considering this particular coordination compound. So if the question is given like this, write the geometrical isomers for this coordination compound. We have to write one cis form and trans form. So as you can see here, it is an MX2L2 type, right? There are two ligands of amine and two ligands of chlorido. Right. So there is a cis form and there is a trans form. So in cis form, what will be is that both this amine or both this chlorido will be on the same side. So as you can see here, this is the cis form. The platinum is in the center. This is square planar, right? That is why we have represented it like this. So both the amine are on the same side and both the chlorido are on the same side. So same side if it is, you will get the cis isomer. Now if you have to form the trans isomer for it, you have to place the both ligands, the same ligands on the opposite side. That means amine, one amine will be here, the another amine will be on this side. One chlorido will be here, one chlorido will be on the other side. So that is called as trans isomer. So I hope it is clear. It is very simple. So if I have to write also M, if I am writing both the X on this side and both the L on this side, this will be your cis isomer, right? Now if the central metal atom is here, one X here, one X here, one L here, one L here. This is called as a trans isomer. Okay, so this is how you write the cis and trans isomer. Clear? Now moving on to in octahedral complexes, how we determine the geometrical isomer. Octahedral complex with formula MX2L4. That means there are two ligands of X and four ligands of L here. Also exhibits geometrical isomers. Okay, so we are going to write the geometrical isomer for CONH3 for Cl2. Okay, so here you can see there are totally 6 ligands which is present. So it is octahedral. Coordination number is of course octahedral, right? So how we can write a cis and trans isomer for this one, where the coordination number is 6. Okay, totally there are 6 ligands. If it was 4, it was easy. On the same side, you can put 2, that will become cis. On opposite sides, if you put, it will become trans. So in this case, you can see there are 4 amine which is written adjacent, and these 2 chlorido will be close to each other. And it is very important, whatever charge is there, that should be also mentioned here. The charge should be also mentioned, right? So if it both comes close to each other, that will be your cis isomer. Now if you place both this chlorido opposite to each other on the opposite sides, that will become trans. See, one chlorido is here, another chlorido is here. All amines will be adjacent to each other, right? Okay, so this will give you the trans isomer. So this is MX2L4 type. Okay, so I hope it is clear. If both the X will come on opposite direction, opposite side, that will be trans. If it comes adjacent to each other, that will be cis, right? Now in octahedral complex of formula MX2LL2. Now what is this LL? That stands for that it is a bidentate ligand. Exhibits geometrical isomerism, where LL is a bidentate ligand. We have already studied, right? There are monodentate, bidentate, polydentate ligand. If it is a bidentate ligand, so for example, we have taken EN here, that is ethane 1,2-diamine. So in that case, how will you write the geometrical isomerism, cis and trans? Let's take the example of COCl2En twice. Okay, so you have to be very careful when you are seeing the coordination compound also. If it is a bidentate ligand, this is how you have to represent it. Again, you can see here both the ethane 1,2-diamine and both the chlorido are adjacent to each other. So this will be your cis form, of course. And if both of them are opposite to each other, right? So one Cl is here, chlorido is here, another chlorido here. One En here, one En here. So of course that will be your trans form, right? So adjacent will give you cis and opposite to each other will give you trans. Now one more thing you can observe here. In all these cases, I've just used a single bond to represent. Now you can see something else which is mentioned here, right? Ethane 1,2-diamine, you can see through 2 bonds I have formed the bond with cobalt. Now why is that? Yes, we already know it is a bidentate ligand, right? It is bidentate. Through 2 atoms at a time itself, through 2 atoms it forms the bond with the central metal atom. So it is very important that you have to draw both these bonds, right? Clear? So if you draw just En and if you put a single bond, it is wrong because it is didentate. It uses 2 of its atoms to form a bond with the cobalt. Okay, so that is why we have mentioned it like this. Clear? Now moving on to the next one. In octahedral complex itself, 2 types we have studied, MX2L4 and MX2LL twice, right? In both this, I hope it is is clear. Moving on to another one, that is MA3B3 type, exhibits another type of geometrical isomerism. So it exhibits facial isomer and meridional isomer. Facial is represented as FAC, meridional represented as MER. Okay. So as you can see here, we have taken this example, CONH3 thrice, NO2 thrice. Okay. So facial isomer means 3 donor atoms of the same ligands occupy adjacent position at the corners of an octahedral face. So this is also octahedral, totally 6 ligands are there, right? So as you can see here, one NO2 is here, another NO2 is here, another NO2 is here, and all the amines are also on the adjacent side. All the NO2 adjacent to each other, all the amines adjacent to each other, and you can see it will be present in the same face of the octahedral. All will be in the same face. That is why this is called as facial isomer. Right. Now, if it doesn't come together, of course, if it is not adjacent, all of them will not come in the same face, right? So then it will become meridional, right? As you can see, one NO2 here, one NO2 here, and one NO2 here, one amine here, one amine here, one amine here. So of course, they are not adjacent to each other. All of them won't come in the same face. So then it becomes meridional, right? So as you can see here, when the position of donor atoms are around the meridian of the octahedron, it will become meridional. So you can remember it like this. If it is all adjacent to each other, they will be forming in the same face, in a single face of the octahedron. That will be facial. They are not adjacent, of course, that is not possible. It will become meridional. So I hope it is clear, right? Now moving on to the next one, that is optical isomerism, which comes under stereo isomerism itself, right? So the first one is geometrical isomerism. We have studied in square planar complex, right, as well as octahedral complex, right? So the next isomerism is optical isomerism. So first of all, before moving on to optical isomerism, what is optical activity? So, or what are optically active compounds? So, optical activity means that for a coordination compound, or any compound, if plane polarized light, okay, so the light, if we pass through a special prism, it will then only move in a particular plane. So only in one plane it will have its direction. Hence it becomes a plane polarized light. So this plane polarized light, if we are passing through a particular compound, the plane polarized light, if it is rotated towards the right or left, we call that the coordination compound is optically active, and this phenomenon is called as optical activity. Right. So how can a compound be optically active? Okay, the compound's mirror image should not superimpose with each other. Hence, in that case, we can say that the coordination compound or the compound is optically active. So let's see. It is a phenomenon in which two complex compounds have the same molecular formula and same chemical bonds. Right. Two coordination compounds, same molecular formula, same chemical bonds, but cannot be superimposed. Okay, so if I am keeping one on top of another, it should not look exactly the same. If it looks exactly the same, that means it is not optically active. If it is not optically active, it will of course not show optical isomerism. So two coordination compounds, if I am superimposing it with one another, okay, keeping one on top of another, it should not look exactly the same. It should not be superimposed. Okay, they differ in the rotation of plane polarized light. That means one compound will rotate the plane polarized light towards the right side, other one will rotate it to the left side. So that is what it will differ in. These isomers are called as enantiomers. Okay, they are called as enantiomers. One will rotate to the right and one will rotate it to the left. Okay, the two forms are called as dextro and levo. Now what is this dextro and levo? As I discussed now, the plane polarized light, if it is rotated towards the right by the compound, it is called as dextro. If it is rotated towards the left, it is called as levo. And these two pairs, okay, rotating to the right and left, these two pairs together is called as enantiomers. Clear? Okay, so as you can see an example here, COEN thrice. 3 plus. This is the example which we have taken here. So you can see this is one form and the mirror image of this will be like this. Okay, if you place a mirror here, the mirror image will be like this, right? So if I am trying to superimpose these two, superimpose means if I am trying to keep this on top of this, of course from here itself you can tell me that this will not superimpose with each other. See here the EN is towards this direction, here it is this direction. So if I am going to superimpose here, of course it will not be the same, right? So this will not superimpose, so of course it is optically active. So in this case, if it rotates towards the right, it is called dextro and levo, and this pair together is called as enantiomer. So this is represented as D, this is represented as L. Also you can represent it as plus and minus. Dextro plus and levo minus. Optical isomerism is common in octahedral complexes involving didentate ligands. Okay, it is generally seen in octahedral complexes. See, this is also octahedral, right? Complexes having didentate ligands, and only cis isomer shows optical activity. So why is this only cis isomer will show? Cis isomer means we have already studied it will be on the same side. So what happens if you are taking a mirror image and then superimposing? Of course, it won't be the same. But if you are taking trans, what happens? Already it is opposite to each other. So if I am taking a mirror image also, if I superimpose it, it will be exactly the same. Right, that is why only cis isomer will show optical activity. So I hope stereoisomer is clear for you. Moving on to the next one, structural isomerism. They again have the same chemical formula, but they have different bonds. The bonds will be different here. So let us see, the first type, it is called as linkage isomerism. So whenever linkage isomerism, you have to remember, linkage isomerism is shown by ambidentate ligands. Okay, so this is very important. It is shown by ambidentate ligands. So which are the ambidentate ligands? We already know, NO2 and SCN, right? So these are the ligands which show linkage isomerism. So it is a type of isomerism in which two complex compounds differ in the donor atoms of ligands. Which atom is in that ligand? Which atom is donating the electrons? Based on that, you will have different two isomers, right? It is shown by complexes containing ambidentate ligands. So this is very important. Ambidentate ligands are present means, of course, it is linkage isomer. So as you can see here, CONH3 5 times NO2 Cl2. So you can see here NO2 here, and if you have to write the isomer, linkage isomer for here, instead of NO2 you write ONO, right? So this is the another isomer for it. So you can see here CONH3 5 times SCnCl2, which will be the isomer. Instead of SCN, it will be NCS, right? It will be NCS. So this is as simple as that. Linkage isomerism shown by only ambidentate ligands. So which are the ambidentate ligands? You have to remember NO2 and SCN. Clear? Right. Coordination isomerism. Next type. Coordination isomerism is type of isomerism due to interchange of ligands between cationic and anionic entities of different metal ions present in a complex. So how you can identify coordination isomerism is that two coordination spheres will be there. So you just have to exchange the ligands and metals with each other. So how we are doing that? Let's see. CONH3 6 times. This is one coordination sphere, and you have another coordination sphere CrCN6. Right. So these two are the two coordination sphere. You have to write the coordination isomer for this. So what you will do? You will exchange the ligands of this. So what you will get? CrNH3 6 times. That is, now Cr is forming, chromium is forming the bond with the amine ligand, and cobalt will form the bond with cyano, right? So that is what you can see here, CrNH3 6 times and COCN6 6 times, right? So in both these cases, just exchange the ligands, okay? Next one is ionization isomerism. In ionization isomerism, two complex compounds produce different ions in solution form. So in solution form means we have already studied in the beginning itself. In solution form, what happens? The counter ion and the coordination sphere will split up. It will give the corresponding ions. So when in solution phase, it should give different ions. So how can you easily identify it as? See, this is one coordination compound given. So if you have to write the isomer for it, just put the counter ion inside and the ligand which is present inside the coordination sphere outside. So you get your isomer. So you can see here CONH3 5 times ClSO4. SO4 is a counter ion here. Now in this case, you can see CO4 comes inside and chlorido becomes the counter ion. So in solution phase, what happens? In here solution phase, your anion is SO4 2 minus. In the solution phase of this, your anion is Cl minus. Okay. So you just have to interchange the counter ion and the ligand. Okay. Ligand goes out, counter ion comes inside. That is your ionization isomerism. The last one is solvate isomerism. It is also called as hydrate isomerism. So how you have to remember this? Based on the water molecules, H2O or aqua. That is why it is called as hydrate isomerism. So let's see. Solvate isomerism is a type of isomerism in which complex compounds differ in the number of water molecules, right, acting as ligands and water of hydration. It is also known as hydrate isomerism when water is involved as a solvent. So let's take an example and understand. CrH2O6 Cl3. Okay, this is one coordination compound which is violet in color, and you can see that now there will be an exchange in number of water molecules. So what happens here is, in the coordination sphere you can see there are 6 water molecules. So in here what happens is, one chlorido comes inside and one water molecule goes outside. That is, it acts as a counter ion now. So it becomes CrH2O 5 times. One water went outside, right? So H2O is here and one Cl came inside. So that Cl is here. Then how many Cl will be outside? It will be Cl2. So this will be grey green in color. Okay. So there will be a change in number of water molecules inside the coordination sphere and outside the coordination sphere. So this is called as hydrate isomerism. So I hope structural isomerism is also clear for you. How can you remember linkage isomerism? Ambidentate ligand shows linkage isomerism. You have to just change the atom which forms the bond with the central metal atom, right? Coordination isomerism, 2 coordination spheres will be there. Just interchange the ligands there, right? Now ionization and isomerism, put the counter ion inside and the ligand outside, right? And solvate isomerism or hydration isomerism, just have to change the number of water molecules. Okay, so I hope that is clear. In the next session we are going to start with the different theories of coordination compounds, which is very important. So in the next class we will be discussing the very first theory, that is Werner's theory of coordination compounds. So I hope the concepts that we have covered in the session is clear for you. So that's all for today. Thank you.